So now we're looking at series.
Series, not Siri.
No, series.
Series.
Series. To understand this, you'll need to know about basic algebra, the distributive property of multiplication,
Which we've met.
and factorising, which we may not have talked about.
Okay.
It's the opposite. And raising to powers, which we've done a video of. What we're doing here, expanding the concept of what we use algebra for. We've talked about using it to, in a previous video, to find what x is, and talked about it as using it as a formula to describe something generically. Now we're talking about how numbers relate to one another when they're used consecutively.
Okay.
And I'll explain what that
series.
means. Yeah, in a series. So this is an example of a series. The dots there, just like in English, mean keep going. So 1, 2, 3. If you were to add all those together, that would be a series. A series technically is something where you you start with something. In this case, we started with 1.
Yeah.
Each time you add 1 to something, and then so you add 1 to that, you add 1 to that, you add 1 to that, and so on. So this is a very simple series. 1 plus, and then you go to 2.
Like counting.
Yeah, and then you add all those together.
So is the series the numbers lined up, or what you get when you add them all together?
The series is what you get when you add them all. Well, it is a description of the process of doing them like that.
Yeah.
And it is also what you get when you add them together.
So the answer, the add them all together, then you would call the number you
would
end
say
up with is
you would
the
say
series.
that's equal to the series.
Right.
Yeah.
Okay. Gotcha.
Now this particular series, there was a German mathematician when he was, I believe, about 10 years old, called Gauss. Lived in about 1800, and his teacher got the class to add those numbers together. A good way of keeping them all amused for half an hour. And in about 5 minutes or less, apparently Gauss wrote on his slate and handed it in.
You got sent out, did you, for being insolent?
Here it is. Here's the answer.
Right.
And the way he did it, he went, because the thing with these series is that there's a lot of interesting. They become very useful. A lot of interesting things about them. The way he reasoned was, well, if I was to add that to another series, exactly the same thing, only backwards. So that now we've got twice the total I'm after.
Hang on, just roll that again. So
we had 1 plus 2 plus 3, etc. plus 99, and now we're going to add that to 100 plus 99, which is plus 98 plus. It's going to be the same thing, just written out backwards.
Okay.
So now we've got both of them.
All right.
So I'm going to find
2 series.
Got two series, but they're going to we're now going to get to double the total we want.
Right. Okay.
But if we add each of those together, 1 plus 100 is going to be 101, 2 plus 99 is going to be 101, 3 plus 98 is going to, etc. It's all going to 98 plus it's all going to be 101.
Right.
And he said, oh, okay, well, therefore we've just got 100 times 101. I know what that is. That's 10,100.
This is what this 10-year-old kid said.
Yeah.
Do you reckon he would have got sent out?
He was Gauss. Probably.
Do you reckon the teachers just would have gone, don't be a smart aleck, get out. Anyway.
Probably.
That's a reflection of my schooling.
Yeah.
Probably
So,
wasn't like that.
we'll go to half of that. 5,050. There we go. That's the answer.
So he just came up with that.
He just came up with that. He was Gauss, and he was one of the world's greatest ever mathematicians.
Far
And he may not have been 10, but
Look, gosh, he was 50.
that was kind of the idea. Yeah, it's annoying even then.
Okay.
But the symbol we use to write this out has a couple of purposes. And one of the purposes of this is to write that concisely. But the really important purpose of this is to intimidate people.
It works.
Yeah.
It's working right now.
So what this symbol has the effect of doing is it divides the world into two camps. The ones who go, I get mathematics, it's easy. And the ones who go, I will never understand mathematics in my life.
Guess which one I'm in right now, looking at that.
Yeah.
It looks like an alien has just landed and scribbled on the screen.
It kind of does. It's a shorthand code. It's not as bad as it looks.
I'll trust you on that.
So we'll break this down. We'll start with the n. N could be anything.
Right.
That's just, we can stick anything in there. In this case, though, for that series of numbers for 1 to 100, we'll just say, well, n is 1. And then what we have down the bottom is this is what we're going to start counting from. So we're going to start counting from n equals 1.
Okay, so what's that weird alien symbol mean?
This weird.
We're getting to that, are we?
Well, this weird alien symbol
Yeah.
is actually the Greek capital letter sigma.
Okay.
Even in about the 1900s, they used to just use an S, but S was getting used for so many things that got confusing. So they started using the Greek capital letter sigma, but like it's like S for summing things up.
Okay. So what's it mean?
So what that means is we're going to start with the number at the bottom.
Okay.
And we're going to add 1 to each time, and we're going to do whatever's there indicated by n, and we're going to add all those together. In this case, we're not doing anything to n, but we're just going to go 1, and then we're going to add 1 to that, plus 2, add 1 to that, plus 3, plus 4. That's what we're doing. And so the S is just telling you to go through that process.
So the S is...
Oh, sorry, the sigma.
The sigma
notation. It means do the calculation, then add to whatever... do the calculation using whatever number you started with at the bottom.
Yeah.
Then add 1 to that number and do the calculation again, add those two together.
Okay.
I'll take you through an example of this.
Yeah, okay.
You can see this happening. And keep going until you get to whatever number we have at the top. Which is 100. So keep...
So is sigma like a it's like a little machine that spins
a little
until you get to the number?
Machine. If it was a computer program, I know you're not a programmer, but if it was a computer program, it would actually be very easy. It would be a loop. It would go, do this, add 1, do the loop again.
Right, okay.
And then add everything. And then
so that's what the sigma symbol means.
It's a little machine saying exactly right. So you add 1 to it, just store that, and then add the next one, do that. That's exactly right.
It's not as scary as I thought.
It's not as scary as it looks. No, not at all. It's so what that means is just what we had: 1 plus 2 plus 3 plus blah, 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 plus 98 plus 99. 100. It's just easier to write that way.
Okay.
I have no idea why they have to. It just makes it confusing to start with the n at the bottom and finish with 100 at the top. But that's just the way it gets done.
Yeah. Okay. It's one of those ones. Once you know that.
Once you know that.
Yeah, I'm with you. There's something visually about it. You stop and work down. But I guess the other way to look at it is start at the bottom. It's building towards the number.
I like that.
There you go. There you go. Well, look at me. It's a mathematician.
And as Gauss worked out over very quickly when he was 10 years old or however old he was, that adds up to 5,050. So yes, it is actually a number, but it's a number that's it's really a machine to generate a number.
Gotcha.
So if we change that slightly, okay, well, let's make that 2n and look at how this works. So we're going to start now with n equals 4. And when we add, if n equals 4, we've got 2 times 4, and then we're going to add that to, now n becomes, so 2 times 4, that dot there means multiplied by.
Yeah.
And then we're going to add that to 2 times 5, we're adding 1 to that. 2 times 6, 2 times 7, 2 times 8, and add all that together. So that's what that symbol means, and we stop when we get to 8.
Because that's what is on top there.
Because that's what's on top.
So the little machine, when all those numbers come out there, is what is happening in response to the sigma.
Correct. Correct. What the sigma command is telling you to do to that 2n. It's telling you to calculate it when n equals 4, then add 1 to your n, then calculate it again, then add 1 and add the whole lot together.
They throw them in movies where they have people writing on blackboards like with space stuff or whatever, and they always throw that sigma thing around.
Especially when they want to intimidate you and go,
you mere mortals couldn't get that. Well, this mere mortal kind of gets it.
Okay, good. Yeah, and it turns out to be a remarkably useful thing.
Right.
So now we're just going to talk about some of the properties that this has. It's got a property called linearity, which ends up being a useful idea. And it's one of those things where it meant one thing originally, and the word persisted. Originally meant, because we're talking about lines, means nothing about that now. It's just become a word, linearity, but it means a couple of different things. One is, if we take that 2n, and we've said it means that, and we looked at earlier in a different video at the distributive property of multiplication, and that works the other way around. So because each of those terms is multiplied by 2, we can take well, that equals 60 if you want it up. But because each of those words is multiplied by, each of those terms is multiplied by 2, we can take the 2 out of it.
Yes.
And if we were to use the distributive property of multiplication, it would look like that. But so we call this factoring out.
Okay.
So we can factor the 2 out of those.
And that. Okay, so you've thrown Mr. Sigma in again with a 2 in front of it now.
That's good.
Oh, sorry.
You're looking ahead.
I had a vision of the future there.
You had a vision of the future,
which will come to everyone else soon.
Which will come to everyone else right now. So what we've actually, that 4 plus 5 plus 6 plus 7 is what you would get from that sigma notation. What it means is that because the 2 isn't being affected by what happens to the n, we can take it out. We can factor the 2 out of the whole thing because it's really just a way of saying we're adding a whole lot together.
Okay.
So
that's back like we were doing before in another video where it's simpler. Is it a form of sort of simplifying
the form of simplifying it? So what that means is in sigma notation, that sigma of 2n means you can take the 2 out. It's still going to be the same thing. You can
okay. You can vaguely get that.
You vaguely get that. The 2n comes out. It looks like that. Is exactly the same as that. So another thing that this means, if we add that, now our sigma is saying 2n plus n squared, that's going to look like that. We're going to have 2 by 4 plus 4 squared plus 2 by 5 plus 5 squared.
Okay.
Because it's a whole bunch of things that are added together, we can change the order. That doesn't matter. So it's going to be 2 by 4 plus 2 plus 5 plus 2, etc., plus 4 squared, etc., which is actually 2 different series. It's a series of...
And you're doing that to kind of... What I experience when you do these processes is it gets simpler and clearer.
Yeah,
is that the point?
It's a way of working with it, way of things we can do with it.
Yeah, okay.
So that first thing means the same as that thing. Basically, that's another way. That's another factor of linearity because things are added, and we're just talking about adding a whole lot of things together anyway.
Yeah,
we can make that 2 different series.
So is the sigma used just in series, or is it a symbol that's used for a whole lot of other stuff?
No, it's specifically for series.
Okay, but
series are used for a huge number of things. That getting ahead of ourselves. But for example. If you want to look up something on a scientific calculator, look up some trigonometry or something, it's not going to store everything in there, it's going to calculate those things using series. So it becomes incredibly important for any sort of mathematical computation for reasons that we'll discover down the track.
I can't wait to watch another sort of nerdy movie like Beautiful Mind or one of those, and when I see that symbol I go, ha, piece of cake, I'm not scared of you anymore.
I know what that is. Now, some fun things with series. So up till now, we've said that adds up to 8. In this case, we've got a series. It's called an infinite series. That sideways figure of 8 means infinite. Basically, it's not a number. It means we just never stop. If we never stop adding that together and just keep going, it's kind of natural to think, well, if you never stop adding it together, then the whole thing's going to result in being an infinitely large number, you would think. But in this case, it's called a convergent series. It's a weird concept, but we keep adding forever, but we reach a limit that it doesn't get past. It stops. This
is kind of blowing the mind a bit here in a nice way. Nice feeling, nice mind-blowing feeling.
This is a mind-blowing feeling. This is a particularly mind-blowing one. If we calculate that out, we get, that's 2 to the 0 is 1, so it's 1 on 1 plus 1 on 2. 2 to the first is 1 plus 1 on 4 plus 1 on 8. And that actually doesn't get any bigger than the number of all things 2. That's simple. It never gets bigger than 2.
So is this one of those where it keeps heading towards it and never gets there?
Yeah. Yeah, so if that's like 2 points on a number line, the first one gets you there, and then every time you get halfway from where you are towards 2,
you're right. And you sort of remember this.
You get closer and closer,
but you never get
past 2, and you can prove that mathematically. But that's a simple visual way to say it.
Oh, I don't know about anyone else, but my brain's just kind of having a little moment there. You know, there's something very cool about that.
There is something very cool about that. Something which is even cooler. This is called the Basel problem. Not Basel as in the not Basel as in the herb, not Basel as in, if any of I'm old enough to remember Fawlty Towers, not Basel as in Basil Fawlty, but Basel in Switzerland, because that's where it was originally sold.
With an E.
Basel with an E.
Yeah, okay.
People figured out, we reckon that's convergent, that's going to stop, but couldn't figure out where. One of the greatest mathematicians ever figured it out. If you spell it out, it looks like that. And what that comes to, of all things, is pi squared on 6.
Oh.
Now, Now, pi's how many times a line across the centre of a circle will go around the outside.
Yeah.
You can't actually express it as a fraction, 3.1, etc., etc. So that thing's got nothing to do with circles, but that comes out to exactly pi squared on 6. Not going to prove that, but if you want to look up the Basel problem on the internet, there's actually on YouTube, there's a lot of videos that look at different ways that gets proven. But but so series can actually kind of give really bizarre and fascinating results like that.
For sure, and ends up coming back to that.
Comes of all things.
Yeah.
Coming back to
spooky.
Pi squared on 6. Kind of is.
Good one.
Thank you for watching.